So now let us just look at some questions that were remaining from last time. So I suppose they were based on when injectivity, or rather, uh, maybe in the end we went to when bijectivity, right? So when bijective bijectivity meaning that sets implies existence of good inverse. So obviously this, let me say this in the case of functions. So I think there was this one question, right? That f is a function from R to R, continuous. Yes, I should not even say existence. I should just say inverse is good. When does it imply? Because if you have bijective, then inverse is there. There is no question. But when is the inverse good? Good meaning that, if it's continuous and continuous, if it's differentiable, then differentiable. So if this is continuous, yeah, then show f inverse, which is like, so is continuous and bijective. Show that f inverse is continuous. Right. So how do we do this? Have you tried this question? Did I say this explicitly?
No, sir. I actually last time I thought it will be in first chapter or second chapter. I read, but I found I I didn't find in book like where should I read first, like what happened in class and then
Oh, okay,
how it
right.
works.
Yeah. So because those things were very ad hoc, so it's very difficult to find in a book. In the sense that that was sort of an original presentation. Okay. Yeah, I'm trying to come. Basically, I was trying to uh, put the basic theorems of analysis, or basic theorems in different places under a language. Yeah, so I was trying to basically set up a language so that some theorems which you have studied in analysis or uh, algebra, okay, can be stated in a uniform language. Okay, so that was my attempt. So that's why it would be difficult. I mean, that's why the class is maybe is important, because it's not directly there in the book like that. Okay. Anyways.
I thought there must be some discussion with Aryan before me. That is must
Sorry.
be I am. I thought there must be some discussion before that, like you and Aryan discussed about it. I was first. It was my first class on that.
Okay.
Algebra.
Yeah, no problem, no issues. Yeah, that's so we can leave that when we can just try to solve this problem. Okay, so you can consider this as just as a homework, and this you will find in any analysis book. So yeah, so we can even if you don't understand the context for now, you will understand and soon. But let us just solve this question. That is a very important question, right? If there's a continuous function from R to R and it is bijective, we want to show that the inverse is also continuous. So, yeah, how do we do such questions? Right. So again, let me repeat that if the context of the question is not very clear, it's not a problem. We can just try to see, just focusing on this calculus question. Okay. And for real analysis, you can follow any Spivak calculus, is a good book. Bartlett and Sherbet is a good book. You can look at any one of them, or any book. Apostle's book is good. So, analysis. But yeah, but let's just do this. So in fact, we will have to do this in a very special way. So first thing is I'll just tell you the steps and you should try to prove this. So you see, uh, F continuous and injective, right? Bijective means at least it is injective. What can you say about this kind of function? Increasing, decreasing, anything? Can you say that it has to be either increasing or decreasing? So it is injective, right? So you can use that. Yeah. So you should show that this is monotonic. This is a exercise in calculus, right? Basic calculus. Continuity and injective means function is monotonic. Okay. So this is, you should prove this. Do you see this intuitively? Is it intuitively correct? Right? Yes, right? Because if it increases and decreases, and then how can it be more injective? It's impossible to be injective, right? But how do you prove it? You have to use some things which theorems which package our intuition into theorems, like mean value. So here it will be just the intermediate value theorem, right? Those are the theorems that sort of package our intuition right into, like, mean value theorem is another place which takes the intuition, uh, right, and puts it into a theorem, right? So here also it is like that, right? So you have to use that and then you see it's monotonic. Okay. So yeah. Now what? After it's monotonic, so I assume that it is monotonically increasing. F is monotonically increasing. Increasing, right? See, this implies that F inverse is also monotonically increasing. Yeah. Again, these are the steps which you must fill in. Prove it. You know the definition of inverse, use it to prove it. It is not a surprise, I suppose, right? This is not a surprise. That if F is monotonically increasing, F inverse is monotonically increasing. You can just prove it. Yeah. Right. So now F inverse is monotonically increasing. So let's just call it G. Okay. Call it G. So G is monotonically increasing. Now G is monotonically increasing. How will you show that it is continuous? Every monotonically increasing function is not continuous, right? It's not continuous. But what can you say? It is something more, right? You have to use something more.
So the map is surjective, then surjective also.
Perfect, perfect. Yes, right. So, no, but yeah, correct. So you are using the fact that G is surjective or something like that, right? Yeah. So F is monotonically increasing, G is monotonically increasing, and it is surjective. Perfect, you got it, man. That's correct, right? I was going to say something else, but what you said is, I think, more accurate for this context. That implies G is a content, and it's obviously you will also prove this. I have not a proof by any means. You have to prove these things, but you can prove these things, right? Only way these monotonic functions are not continuous is when they are not surjective. If it's surjective, then it becomes continuous. You can prove it. So you can prove these things, right? Yeah. That's all. That's it. This is all that is. this combination. So it basically packages all the calculus you have learned about continuity so far. If you think about it, this is all you know in continuity, right? Some definition and these things. Means on the level of theorems, not saying that this much knowing will help you to solve all problems, but it uses all the elements of continuity which you have learned. And similarly, the question about differentiability, which we'll discuss next day, also combines all the things you have learned about differentiability to prove in differentiability of the inverse under suitable conditions. Okay, so let me not ask that question also. I'll just ask you to fill in the gaps of this. And best place will be to look at Spivak calculus. For calculus, I always recommend Spivak calculus book. Okay, if you are starting out, it is good. And with any book, that's up to you. You can use. Okay? Yeah, so with that, I'll stop. As I said, I'm stopping a bit early today, means compared to when I started. Yeah, but that's how
Okay, sir.
it has to be this time. Next, we are meeting. Yeah, so next we will meet Sunday. For Virendra, we'll be meeting on Sunday, and for Nagesh and Aryan, the timing is Saturday morning. Okay, where we are doing something else. Yeah. So, yeah. Okay.
Sir,
Yes.
sir, I solved that problem. X raised to n is equal to x in ZP
X x raised to n.
is equal to s x
Okay, right. In
in Z
ZP.
in Z.
In ZP. Right. Okay. So so how this is
I
a
solved.
good problem. Okay, yeah. So then this is basically you're saying this is this modulo p, right? Yeah. Okay. So since you have solved it, I'm not asking you for the solution right now, but you can try to apply this, right? I'll ask you some applications. Maybe you can try that. Yeah, let me ask you for some applications. You can use your newfound knowledge somewhere, right? Where can you use this? Mm, yeah, I think we don't have enough things to use it right now. Uh, so if I'm looking at polynomials, can I ask something there? Just give me 1 minute. So this fact is elementary. This is called Fermat's little theorem in number theory language. It's very, very important fact in number theory. And mm, so I want to look at polynomial. Let's say if I take a polynomial in 3 variables. Okay, take a polynomial in 3 variables. Now I am asking, yeah, polynomial in 3 variables and the coefficients are in ZP. Take. If you want, you can take 1 variable. It's up to you. Okay. Coefficients are
Okay,
in
sir.
ZP and let's just take 1 variable. It doesn't matter. Yeah. So you look at this polynomial and you look at this polynomial. This is the polynomial you get by raising it to the power p or multiplying it p times. Okay. Now if right. So okay. So now show that if a1 comma a2 comma a3 in zp, so just roots, this is a root, so basically these 3 numbers are in zp. Okay, and if it's a root, show that this is a root of f if and only if Uh, this is a rubbish question I'm asking. Sorry, this is not even a question. Let me just find it in the book. Or leave it. I think. Yeah. Sorry. Yeah. Sorry. Sorry for the mess. Yeah. Yeah. Let us leave it for the time being. I am not very. So what happens if I have a polynomial, I raise it to the pth power, then from what all the knowledge you know is that the coefficients do not change. Okay, but the power changes. Okay, so yeah, then I am just saying that yeah, but that doesn't actually this question is interesting, but you have to extend this to from ZP, you have to go to some better structure to ask a question. Otherwise, the question becomes a trivial thing. Okay. But maybe you can try this. Uh, you can show that this is divisible by something. This one I forget. Uh, Wollstonecraft's theorem. Just a second. This is not good here written properly. Hmm. Oh, damn, what is this? Okay, this is yes. Yes. Right. So try to prove this thing. This is what I was looking at. Yes, try to prove this thing. Try to prove this thing. Prove that this is congruent to, so it is obviously not divisible. This is congruent to this. Okay. Yeah, try this. This is an interesting question. This is elementary also, but with this knowledge, you can probably give a easier proof. Yeah, show this. Okay. Yeah.
Yes, sir.
So n and m are
So,
integers, p is a
sir,
prime. Sorry.
okay,
Basically, I'm saying that in
okay,
ZP, these two things are equal. Okay.
okay, fine.
It's a very interesting thing that in ZP you can basically forget this. That's a beautiful identity. That's why it's a beautiful identity. Okay. Yeah. All right. So then we'll
Okay.
stop here and we'll meet it. Just note that down. Yeah. All of you can try this question. Okay.